Okay, so let's wait for 5 more minutes to see if anybody else joins. Then we can start. Okay, so welcome everyone. Let's start. Uh, Please let me know someone that whether you are able to see the screen or listen to me. Okay, fine. Okay, so welcome. This is NOC EE-91 NPTEL tutorial on semiconductor devices and circuits. The course is offered by Professor Sanjeev Samvandan. I am Debashish Nandi from IIT Kanpur. I am a TA assigned to this course. So this is the time where we go live every week, 5 to 7. You is you have another session from 3 to 5 for the same course, but the contents myself and Atiba are assigning such a way that it doesn't overlap for the same day. Okay. So again, I would like to reiterate the prerequisites that you are expected to at least have gone through the previous week lectures so that at least you can follow this tutorial session. Also, the week 2 assignment for this week, I am expecting that you have at least have a look on it, have a look into it, and have at least tried some of the problems. Okay, it will be helpful to you. Also, please keep your microphones muted all the time, and unless I am asking you to answer for something, or you can chat your queries, which I may answer or during the question or during the problem or at the end of the session. Okay. So after the second hour, I'll give you some time so you can ask your general query. So also the link of the recorded session will be shared with you by the NPTEL team. I'm not sure whether it has already been shared. You can find it on the course web page also if it has been shared. Okay. So this is week 2. So let's begin. Okay, so last week I could not complete one problem, so I will start with that. So let us go through the problem. What it is telling that consider a particle of mass m moving in the one-dimensional potential. Some potential function is given for mod x less than 1 like this. Okay. First, any of you can tell me what does this function mean? Any of you are aware of this Dirac delta function? You can unmute and tell me.
It's a unit function?
No, it's a Dirac delta function, right? Let me just tell you. Whatever you are telling, that function is like if it is your x and it is your u of x, that is like this, you have
It exists
this.
only on x is equal to 0.
Okay, so what
Elsewhere
is
it
the
is 0.
amplitude? So this is
1.
amplitude is 1.
Not x is equal to 0.
Okay, just go. Let's go one by one. So this is an unit step function, right? You are aware of it. You must have studied it in your signal systems course, right?
It's infinity at x equal to 0.
Right. But let's go step by step. This is the function I have drawn. It is a unit step function, right? Are you aware of this function?
Yes, sir.
Okay. So just tell me what happens if I take derivative of it.
Impulse.
Yeah, but how does it happen? You see, in this region, the value is constant, right? So the derivative will be 0, right? And in this part also, the value is constant. So the derivative should be 0. But, sorry. So the derivative should be 0. So what about at x equal to 0? It has a hard change, right? So the derivative doesn't exist at this point. So mathematical manipulation of this is that we tell it that at x equal to 0, we have a infinite amplitude. Okay. And this is defined by this delta function. So the definition of delta x is that delta x equal to infinity at x equal to 0. And can you please mute yourself, Parth Sarathi? Okay, thank you. And so what happens at other points? It becomes at x not equal to 0, it becomes 0, right? So this is a kind of delta function. So someone was telling me that this function is unit function. So it is not an unit function. It is the derivative of an unit step function. Okay. And what is the property that if you integrate it throughout, so it will give you 1, right? Okay. So let's proceed with the problem. In the problem statement, it is mentioned that you have a potential profile like this. Just let me add one page. So you have a potential profile like this. So this is your A delta X. This is anyhow infinity. This is X equal to 0, X equal to A, and this is X equal to minus A. Okay. So what do we mean by mod X less than minus A? It means that minus A less than X less than A. Okay. These are the same thing. So can you tell me what is the y-axis here? Anyone? This we have discussed in last session, right?
That is energy.
Energy, right? Okay. And these values we are talking about the potential energy, right? This Vx is the potential energy. So now what did I tell you last time? If this kind of problem arrives, what should we do first? What should be the first step? Because there are many ways to solve, right? We have to follow some systematic approach so that you can solve any problem of such kind. So what is the first step?
Outside boundary 0 equate with
No,
0.
no, that is not the first step. One step back. When such a system is given to you, what should you do first?
Schrödinger equation लिखते हैं.
Right. But what is the first step? First step is that, see, understand this again very carefully. First step should be when such a system is given, you need to define the boundaries and you need to define the entire problem into regions. Okay. Then you proceed for the whatever steps you are telling about. So first step should be, let us define the regions. Okay. This is region 1, region 2, region 3 and region 4. Can you see the 4 distinct regions? I think you should be able to see, but understand this very carefully and remember this for the entire of your life. Okay. If a large problem comes, break it into smaller problems, your life will be easier. Okay. So again, for region 1 and region 4, we know that my psi 1 is equal to 0 and here psi 4 equal to 0, right? So these two regions we should not be worrying about. And here we need to find out what is my psi 2x and what is my psi 3x. Okay. So let's go step by step. Let's take region 3 first. Okay. So let me write the Schrödinger equation. Then next step should be writing the Schrödinger equation for a particular region. Okay. This is the Schrödinger equation. So and region is like 0 less than x less than a. Okay. So what is the value of potential at this point? Potential is 0. And in the question it is given that we need to find out for a for the case where the energy ground state energy of the system vanishes, means it becomes 0, right? So that means my E is also 0. Did you get it? Why I am putting V and E both 0? Because V is 0 from the condition of potential at this place, my V is 0. This is 0. And E is 0 because I want to find out the solution for the case for which the ground state energy vanishes or becomes 0. So what do I left with? This is my constant term, right? So it is not equal to 0. So I can always write that del square psi by del x square is 0. So I can write the solution in this form, b1x plus c1. Is it okay with you from this step to this step? Anyone? Any difficulty in understanding this? That in last session also I was writing directly from the differential equation the predictable solution. It should be pretty clear, right? Because if you take the double derivative, you see that first time it will come b1 constant and then it will go up 0, right? So I can b1 and c1 are the arbitrary constants. Okay. So similarly for region 4, minus a less than x less than 0, I have this solution. Let's say b2x plus c2. Fine. So this is my psi 3x, this is my psi 2x. Fine.
Sir, is that region 2 or 4, sir?
Sorry,
Is this for region 2 or 4?
which one?
This second equation.
That is, oh, the constants b2 and c2.
No, sir, this equation is for which region, sir? Either 2 or 4.
This region, you see, this is region 2, this is region 3, right?
Okay, sir.
Okay, so you have these two solutions now. So what is the next step? You have solutions in terms of arbitrary constants. Now we need to find out the constants, right? So how to find out the constants in any linear equation? We need to use some boundary conditions, right? So what should be my first boundary condition? What are my boundaries? This is one boundary, this is one boundary, and this is one boundary. So if you see that my psi 3 of A should be equal to psi 4 of A. This is x equal to A. So what about my psi 3 of A? That is B1A plus C1 is equal to what is psi 4 of A? Psi 4 of A is 0. So my C1 is equal to minus B1 of A. Fine. So my equation becomes B1 of x minus B1 of A, x minus A. Okay. This is my one equation. Let's mark it as A small a. Similarly, psi 2 of minus A should be equal to psi 1 of A minus A at this boundary. So your B2 into minus A plus C2 should be equal to 0. So your C2 should be equal to B2 into A. Fine. So your psi 4, not psi 4. So your psi 2 x should be B2x plus B2A. That is your B2 of x plus A. Okay. So now we have got two constants to figure out, right? C we have found out in terms of B's. Okay. So now you see we can apply boundary condition at this place also, x equal to 0. So what would that lead to? That psi 2 0 should be equal to psi 3 0. Okay. Then from these two equations, we can just put x equal to 0. We will have minus b1a is equal to b2 of a. That means your b1 is equal to minus b2. We have found another relation. Okay. So now let me call it b. Say it is b. Okay. So what are my equations now? My psi 2x is equal to b of x minus a for minus a less than equal to x less than equal to 0, and my psi 3x is equal to this will be b2 will be, what is my b2? Minus b, right? So minus b x plus a for 0 less than equal to x less than equal to a. So what is my psi of 0? Psi is the overall continuous function, right? We have broken down psi into 4 parts region wise. The entire wave function is psi. So psi of 0 is, you can see that it is the same, minus b of a. Okay, so this we note now. Then what is the next step? We were asked to find out the value of this a, right? So what will you do? We will write the Schrodinger equation again. Plus v of psi equal to e of psi. Okay, so you see that around x equal to 0 there is a discontinuity. Okay, there is there is a delta function. So we can use this property of delta function. Generally what we do normalization integral to find out the coefficient of the wave function, right? So similarly, in this way, let me integrate this function from 0 minus to 0 plus what was my v? V was my a of delta x, right? And this is my psi of x dx equal to, and for which energy state we want to find out the solution? For e equal to 0, right? So this will be my 0. So can you tell me what will be this? This will be nothing but my d psi by dx, right? Double derivative integrated once becomes single derivative. Okay, plus can anyone tell me from your signal system knowledge what this thing should be? Anyone? This is a particular property of delta function is to be used here. So anyone can unmute and tell me that what should I write in this place?
Is it minus? It is 1, sir.
How should it? Why should it be 1? There is a function of x, right? So
Psi of 0.
psi of 0, right? So if you didn't get it, so suppose if you have a delta function of x minus a into fx dx, okay, this becomes f of a. This is the property, remember? Okay, so using the same property, we can write down this, and a multiplication will be there. Okay, so now what happens? Minus h bar square by 2m. So this is, I can write psi dash 0 plus minus psi dash 0 minus psi dash is nothing but d psi dx plus a of, what was my psi of 0? Psi of 0 was minus ba, right? So minus ba equal to 0. So can you tell me that what is my psi dash 0 bar from this? See, for this was my region, right? This is x equal to minus a, this was x equal to 0, this was x equal to a, right? So 0 minus would be around this region and 0 plus would be around this region. Let's say this is 0 plus and this is 0 minus. So what function was valid at this place? Psi 2, and it was psi 3, right? So psi dash 0 plus would be nothing but d psi 3 of dx at x equal to 0 plus, right? So from these two equations, you can see that Did I jumble up in the nomenclature? Yeah, I think this should be psi 3, right? This is psi 2, right? This is psi 2, psi 3. Okay. So what happens now, that your psi dash 0 plus is nothing but your b. If you just get d psi 3 by dx, it is nothing but your bx. Sorry, it is nothing but your b, right? And this is d psi 2 by dx is equal to minus b. So it is b minus of minus b plus minus a b equal to 0. So what do we have? We have that minus h square by 2m into 2b is equal to a into b. This gets cancelled, this gets cancelled. So what is my a? A is nothing but h bar square by m into a. Okay. So is there any option? Yeah, C is your right option. Okay. So please tell me if any one of you didn't understand this solution, or any part you want me to repeat. Okay. So let me ask you a question. What are the properties of this wave function? Last class we have discussed, right? Anyone can unmute and tell me what were the properties of this psi of x?
It should be continuous. Derivative also should be continuous.
Okay,
And
wait. That's all. Good. Derivatives should be continuous, right?
yes, sir.
So do you see that from these two, the derivative is not continuous at x equal to 0?
Yes, sir.
Why does that happen? Then we are violating that, right?
Yes, sir.
So can you throw some light why that is happening? Are you getting that why that is happening?
And sir, due to impulse function.
Yeah, exactly. So remember this, the main point of solving this problem is this only. Whenever you encounter a delta, whenever you encounter a this kind of delta potential, okay, remember that your wave function will be continuous around it, but the derivative of your wave function will not be continuous around it. The condition of psi, that psi should be continuous and its this derivative should be continuous for the real cases. This delta function, delta potential you cannot achieve, right? At any in physical sense you cannot achieve this delta function. So it always remember, in any of your exam problem or in future research problem, if you encounter that there is some delta potential, okay, then remember that the wave function is continuous around it, but the derivative is not continuous. Okay. So this is the point I wanted to make. Okay. So let's move on to the next problem. Okay. So it is asked that number of lattice points per unit cell is in a body centered cubic lattice is, okay. So what is a unit cell, by the way? Anyone can tell me.
The smallest structure of the crystal which repeat periodically
Why should it repeat periodically?
to make crystal.
So crystal has inherently it has periodicity, right?
Yes, sir.
Okay. So okay. So suppose these are the atomic points. Okay. and let's say this is the region I am talking about. So yeah, Tanish, the answer would be 4, but I want to tell you that some more stuffs on this. Okay, it is just not sufficient to solve the problem. Numerical solution we all can do, but it is good to understand the things in further in depth. Okay, so this is one stuff, and let me just that. So can you tell me what is what types of material? I think this was taught in the class also. Okay, so this has periodic arrangement of atoms, right? Means this distance and this distance are same. So if you can construct this and repeat it multiple times, so you will get the
Limitation.
entire crystal, right? So this is your crystal, and what is this? Regions are crystalline.
Polycrystalline structure.
This is polycrystalline, right? So your silicon is your crystal, okay? And what is your polycrystal? For example, is your polysilicon, okay? So if in your silicon you dope it very heavily, say silicon's atomic density is what? Can anyone tell me? Atomic density of silicon? Okay. By the way, these numbers you should be familiar with, okay?
2.3 gram per centimeter cube.
Atomic density 2.3 gram. No, that is the density, right? Atomic density is your how many number of atoms are there in per cubic centimeter of silicon. Okay. So you can dope it up to around 10 to the power 19 per cc. Okay. So this will you will learn in the future lectures. Okay. Just let me tell you one thing, that if you try to dope this with some boron or phosphorus, let's say 10 raised to 20 or 10 raised to 21, so the crystalline nature of the silicon breaks down. Okay. It starts to become a polycrystalline. And what are these called? These boundaries?
Grain boundaries.
These are called grain boundaries, right? And why are these important? These play into your scattering process also. Okay. When the electrons are moving in the crystal, so they can get scattered by from these grain boundaries also. Okay. And this is your nothing but amorphous. Okay. Means there is no such periodicity and all at all. For example, is your silicon dioxide. Okay. All of these elements you will find in your modern devices like your MOSFETs and all. Okay. In MOSFET, you have this kind of stuff, right? Let's say this is your source, this is your drain, and this is your gate. So generally your gate is made by polysilicon. Source and the say entire MOSFET base is made of your silicon, and you say this oxide part is your silicon dioxide. So you have all of this. So it is very important to understand the physics of all of these structures. Okay. So that's why this part were introduced in the course. Okay, so now we will talk about crystals only, bulk silicon crystal. Okay, so in crystal, as someone has rightly said, that unit cell is the smallest thing which can, if replicated, can make the entire crystal structure. Okay, so there are in 3D there are 14 types of this structures, crystal structures, and in 2D if you say there are 5 kinds of structures. Okay, so we mainly are considerate about 3 special kinds of structures. Okay, these are called simple cubic, face centered cubic, and your body centered cubic. Okay, this is FCC, this is BCC. Okay, so what is a simple cubic? As you can understand from the from the nomenclature, that the atoms will sit at the corner. Okay, so can you tell me that how many atoms will be there in one unit cell for a simple cubic?
One atom.
How?
8 corner atoms are shared by 8 other unit cells. So the effective number of atoms per unit cell will be 1.
These are the number of atoms. These are the share. Okay, so I just wanted to ask, does anyone have issue with visualizing that one atom is sharing with 8 other cubes? One atom is shared between 8 other cubes. If you have that doubt, please tell me at that point, at this point only, if you have that visualization issue.
Yes, sir. I have.
Okay, you have the visualization issue, right? So you see that this is a ball, right? These atoms are spherical in nature. Okay, so in 3D, in 2D, if you see that it has four shares, right? If one atom is shared at a corner, you see how many this will be shared by this cube also. So who was that? Tanish, right? So Tanish, please unmute yourself once.
Yes, sir.
So this atom can you see that it is shared between 2 cubes?
Yes, sir.
So now if I draw that there is another adjacent cube, now can you see that this atom is shared between 3 cubes?
Yes, sir.
Similarly, you will have here also one cube, so this will be shared between 4 cubes. Similarly,
Yes,
out of the paper there will be also 4 cubes.
Yes, sir. Yes,
So
sir.
you see one atom at the corner point, one atom, this volume will be shared between 8 cubes. Okay,
Yes, sir.
so when we are talking about a particular unit cell, let's say this unit cell. Okay, so what is the contribution of this atom to this unit cell? If I talk about this atom only,
1 by it was.
1 by how many number of cubes it is sharing, right? That is, it is sharing with 8 number of cubes.
Yes, sir.
So for one particular unit cell, its share is 1/8.
Yes, sir.
So that's how this share part comes. And what is 8? 8 is the number of points. Okay, so you have 8 atoms. Each atom has a share of 1/8 to the particular unit cell.
Yes, sir.
So now do you get it? How this one is the answer, that one number of atom per unit cell is there?
Yes, sir. Thank you.
Okay, now you only answer me the next thing. Let's go to the face centered one. Okay, so what is additional in face center? But first of all, you notice that it is also cubic. Okay, so you have 8 corner atoms, that is from this cubic term, and another one is face centered. Okay, so how many faces are there in a cube?
6 faces.
6 faces, right? So face centered would be just let me do this. Okay, so let me take the top face. So face center would be the wherever the diagonals are crossing of that face. Okay, So
Yes.
this is one atom. Similarly, you have 6 faces, you have 6 more atoms, right? If you take the diagonals and get it cross section at each point, so you will have these 6 atoms, okay? So how many atoms are there in a unit cell for FCC if we do not consider the share?
6 1 by
6
6.
corner, 6 face-centered face atoms
Yes, sir.
plus 8 corner atoms, okay?
Oh, okay.
So now number of atoms per unit cell, you need to take into account that one atom is shared between how many cubes, right? Or how many unit cells. So these 8 corner atoms, you know that these are shared between 8 neighboring cubes, right?
Yes, sir.
So this much you know that for corner atoms there will be a contribution of 1, right? 1 atom in total.
1 atom.
And for this face centered, can you tell me between how many unit cells these are shared?
How many unit cells? Face. I'm not.
Okay, just understand this way. This is one unit cell, okay, and there is another unit cell beside, okay. So there is a face centered atom at this
Faces तो
location.
6 ही रहेंगे.
Sorry?
Face 6 ही रहेंगे.
Yeah, face will be 6, right? I am just talking about one particular face, okay. Let's take out of 6, let's take 1 atom, then we can multiply it with 6, okay. 6 into 1 into, we want to calculate the share for 1 atom, okay. Just the way we did, we took 1 atom of the corner atom and understood that it is shared among 8 cubes, right? 8 unit cells.
Yes, sir.
Similarly, a face, a plane is shared between how many unit cells or how many cubes?
2
cubes,
one
right?
face.
One face is shared
cubes.
between 2 cubes. So
Yes,
an atom sitting at the center of the face is being shared by 2 adjacent unit cells, right? So this
Yes,
share would be nothing but 2, right?
Yes,
So what would be the total number of contribution? Due to the face atoms we have 3 and due to the corner atoms we have 1. So 4 atoms per unit cell for FCC, okay? So
yes.
you understood, right? You will not forget this thing.
Yes.
Okay, so now let's move on to the third kind or the body centered one, okay? So what is a body diagonal in a cube and how many body diagonals are there? Can anyone tell me? What are the body diagonals of this cube? First of all, that there will be 8 atoms at the corner because this is also cubic in nature, okay? Anyone can unmute and please tell that what are the body diagonals of this cube?
BE.
Huh?
BE is the body diagonal.
BE is a body diagonal, okay? Right?
CH.
CH is a body diagonal, right?
DG.
AG, DG. DG is a body diagonal and AF is a body diagonal, okay? So, Tanish, did you understand this?
Yes, sir. It's
The body
center.
diagonals. So
Yes,
body, so it is basically the center of the cube. Okay.
Yes, sir.
So let's say there is another atom. Okay.
Hmm.
So now can you quickly tell me that what are the number of atoms per unit cell for
I
this
will-
BCC? Again, go step by step. How many types
Oh,
of atoms you have? 8 corner atoms
8 corner spaces 6.
plus 1 center atom,
One.
because there is no face, right? It is body centered cubic.
Oh,
Okay. So 8 corner
yes.
atoms, what is the share of one atom? Is 1 over 8.
1 over 8.
And what is the center atom's share? 1 over?
Hmm. Hmm. Diagonal atoms कितने हैं?
No, no.
4 होंगे.
This, no. This body, see, again, the question is that there is one atom at the center of the cube. Okay.
Yes, sir.
So that atom is being shared by how many unit cells? वो जो एटम
1.
सेंटर में है वो कितने यूनिट सेल्स के बीच में शेयर हो रहा है?
There is 1 unit cell. Like,
It belongs to the parent cell only, right? It is not
yes.
being shared between any other cells because it is neither on the edges, nor on the faces, nor on the corners.
Yes, sir.
So it will be one only, right?
Yes, sir.
So what are the, how many atoms do you have? You have one from this and one from this, so 2, right?
Yes, sir.
So body diagonals for per unit cell we have 2 atoms.
Yes, sir.
Face diagonals we have 4 and simple cubic we have 1. Okay. So
One.
our question was that number of lattice points. By the way, lattice points are wherever these atoms are located. Okay. So number of lattice points per unit cell in a body centered cubic lattice is 2. Okay.
Yes, sir.
Okay. So I think you will not forget this, that how to go about it. Okay. Don't need to remember anything. Just draw a cube, and then from the nomenclature, if it is body centered, remember that it should be the at the center, because the body diagonals should be where the body diagonals intersect. At that point, you need to have an atom. Similarly, for face centers, you have to have the atom at the center of the face or the side. That means where the diagonal of the faces are getting intersected. Okay. So let's
Yes,
move
sir.
on to the next problem. Okay. Another thing is that uh, here we are talking about that there is only one atom at a lattice point. Okay. So these kind of things are called monoatomic crystals. That means at one lattice point we have only one atom, but it is very rare, or very few materials or crystals will be there which are like that. Most of them has multiple atoms, okay, at the same location. So this thing we called a basis. So whenever someone is called your basis is 2, that means at one lattice point you have 2 atoms. Nothing, you just need to consider instead of one atom there will be 2 atoms. Similarly in the here also there will be 2 atoms if the basis is 2. Okay. And there will be some cases, even there are some materials also where you may say that the body centered one may have a basis of 1, but the corner atoms may have a basis of 2. So those cases are also there. So moving on to the next question. So the question is that gallium arsenide has a zinc blende crystal structure. So what is zinc blende? Zinc blende is nothing but FCC. Okay. Just the atoms are more than one type of atoms will be there. Okay. So let's draw out the FCC. It has 8 corner atoms and 6 face centered atoms. Okay. 6 face centered atoms. These are nothing but one I am showing, that the diagonal intersection locations. Okay, so we have seen that number of atoms in an unit cell for FCC was 4, right? Again, 8 corner atoms 1 over 8, 6 face atoms 1 over 2, right? 3 plus 1 equal to 4. So what is the basis? Lattice with 2 atoms per lattice point. So basis is your 2. Okay, means here you have 2 atoms at each location. So what would be the total number of atoms per unit cell? Per unit cell is your nothing but 4 into 2, right? 8. Then they are asking us that they are telling that assume a lattice spacing of A equal to 5.65. What is the lattice spacing? Lattice spacing is this one, spacing between two lattice points. Okay, in an unit cell, the unit cube. This is 5.65 angstrom. Okay, so A is your 5.65 angstrom. That is 5.65 into 10 raised to minus 10
Why
meter.
basis is 2, sir?
Because it is given, right? Gallium arsenide has a basis of 2. Means that it has the physical nature in that way.
Okay, sir.
It has nothing to do with that. Why the basis is that? Yeah, I can answer you that also, but that will take more depth, right? That requires more depth of understanding about the crystal structure and your crystallography. Those kind of stuffs will be required. Your molecular orbitals and all. Okay, so I'm not going into there. Just understand that the in real life the atom is like that. Okay, so then this is your lattice spacing. Okay, this is meter, this is centimeter. Okay, angstrom to centimeter is 1e minus 8, that means 10 raised to minus 8. Okay, and for, by the way, remember these notations also. Okay, 1e 10, 1e 10 means 10 raised to 10. Okay, so these are the scientific notations. So this is you have. So what is the volume of unit cube? It's nothing but A cube, that is 5.65 into 10, 5.65 into 10 raised to minus 8 cube. Cc means centimeter cube, right? Just let me write centimeter cube only. Cc is cubic centimeter. That's the same thing. So how many number of atoms per cc are there in a gallium arsenide, right? So we see that 5.65 into 10 raised to minus 8 raised to 3 centimeter cube of gallium arsenide holds how many atoms? Anyone?
8 atoms.
8 atoms, right? So 1 centimeter cube of gallium arsenide hold 8 over 5.65 into 10 raised to minus 8 atoms. So you will have the answer that it will be around 4.4 into 10 raised to 22 atoms. Okay, so this will be your right answer. So please tell me, anyone, if you did not get it. I will repeat any part. The purpose of this session is that you understand whatever you are not getting understood in that lecture series. Okay, so if you have any doubt, please don't take home with any doubt from these sessions, either of mine or Atif's. Ask questions. Okay, I think this is pretty straightforward. So let's move on to the next problem. Okay. X-rays of wavelength this angstrom undergo a second order reflection at a glancing angle of this from the crystal. Find the spacing of the atomic planes in the crystal. First thing, tell me, did you read about X-ray crystallography or Bragg's diffraction law?
No, sir.
Okay. Anyone else?
The experiment aims at finding the lattice constant of the crystals by passing the
Okay.
electron beam.
So you have read about this, how that works, how that formula came about? Else I will explain.
The concept was in the lecture slides, so I told.
Okay, one more thing. Please don't go through the lecture slides only. Okay, listen to the lectures also, because the professor annotates so many things on the screen to make you understand, which you will not get in the lecture slides. Okay, so it is better to go through the lectures itself, then refer the lecture slides when you are making notes and something else. Okay, remember this. So anyway, let me just explain. Okay, so okay, how do I draw the planes? Okay, just this is one plane, this is another plane, this is another plane. Okay, so let's say, so this is one plane. Okay, this is another plane, and this is another plane. And how the atoms are arranged? How the atoms are arranged? Let me say atoms are arranged like this. Okay, this, this. Again, bottom, this. Okay, so these are the crystal planes, let's say. Okay, these are crystal planes. Okay, so now if I look from here, top view, what will I see? This is say plane 1, this is say plane 2, this is say plane 3. Vertical planes. Okay, these are the vertical planes I am looking on from on top, so I will see a straight line only. Okay, so this is for plane 1, this is for plane 2, this is for plane 3. This is nothing but your top view. Okay, did you do you have any understand visualization issue from this to this?
No, sir.
Okay, fine, that's great. So now I'm just drawing this thing again here. So what does happen is that, just let me, suppose here is a electron gun. Okay, this is some electron gun, and here is some screen. Okay, where you see the interference pattern. Okay, so one wave is coming at this location, another wave is coming at this location. These are the electron beams. Okay, it gets diffracted and going like to this way. These points, by the way, are the atom locations. Okay, the lattice locations, lattice points. So These are the electron beams, and here you will have certain kind of radiation pattern. Okay, so this angle is theta. Can anyone tell me what is the incident angle if this is theta? Come on, yeah, you guys have read about reflections, refractions, right? In optics.
Incident angle is theta.
No, incident. How can incident angle be theta? What was the incident angle in a reflection you studied? This is a plane, right? This is a mirror. What was the incident angle?
Sorry, it is 90
Angle
minus
with
theta.
90 minus theta, right? So these things you need to visualize, okay? So incident angle is 90 minus theta. So remember that this is not incident angle, okay? Whenever there is given the angle is given in the question that the incident angle is something, just do the 90 minus theta thing, okay, to get that this angle, this glancing angle, okay, this is called glancing angle. This one, glancing angle. So now what we do? Okay, so now there are two waves, okay. When do we have constructive interference and when do we have destructive interference? Can anyone tell me?
When same phase constructive, out of phase difference 90, destructive.
Right.
Sorry, 180.
When
Same
the
phase.
minima and maxima occur at integer times pi, we will have
Right.
constructive
The
interference.
peaks should match and the throughs should match, right? Then it will have a constructive interference. Suppose if you have this as the magnitude is between this plus minus a, and it is also having a magnitude between plus minus a, then if these are at the same phase, the peaks and valleys, then the resultant wave you will have a this kind of shape, okay. And what will be this? This will be 2a and this will be minus 2a. This is called constructive interference, okay. And what about destructive interference? Destructive interference is nothing but that you will have a wave like this, okay. So peak value of this is matching with the peak of this, right? So what will you have? You will have a just zero line, this zero line. If you add this black and this blue wave, okay, that is called destructive interference. Now tell me one thing, that suppose this is your wave, okay, and I am pointing out to this is one distance, this is another distance, okay. So if the wavelength is equal to lambda, so what are this distance d1 and d2 in terms of lambda? Can anyone tell me?
D2 minus D1.
No, not d2 minus d1. d1 individually and d2 individually.
D1 is lambda by 2.
d1 is lambda by 2. d2 is
Lambda.
d2 is lambda, right? So you see, for this blue and this black, okay, for these two waves the difference was of this same point. Let's say these are the same points. This is point A and this point A is shifted, the phase is shifted by 180 degree or this much amount, okay. So what will you have? The valley and peaks are matching, giving you destructive interference, okay. And this shift is lambda by 2. And again, if we shift it by another lambda by 2 for the red curve, let's say A point is now at here. So how much the point A is shifted? It has shifted by a lambda distance, right? For constructive interference. So now tell me that is it necessary that I need to have a difference of the same phase front or phase point a small a to have a difference of lambda only? It can be any integer multiple of lambda, right? Because this point, if a is now here, then also I will have a constructive interference. This a is moving this way, okay? So basically, if the phase of the two waves are different in such a way that a particular point on the wave and same point for the next wave are different, differed by n lambda distance, then I will have a constructive interference, okay?
Yes, sir.
So this much you have understood, okay? Now let's go back to this diagram. Let's say this distance is d. So d is nothing but my lattice constant here, right? If you make a cube out of it, you'd see that this is nothing but your a distance, okay? This distance is what I'm talking about, d. That a was now d, okay? So this is the lattice constant d. So now tell me, let's say this is my wave 1 and this is my wave 2, okay? And let's draw some perpendicular line. This is a perpendicular line to this, okay? So just I am stating something, you just tell me whether you agree or not. The wave 2 has traveled this much more distance. Do you agree? Than wave 1.
Yes, sir.
Tanish, do you agree?
हाँ sir.
The wave 1 has traveled this much because how can you say that this distance are same, right? That means your this distance and this distance are same. Similarly, this distance and this distance are same. But this much one, whichever I have highlighted here, this much part, the wave 2 has traveled additional, okay, extra. That means this is the difference between the same phase fronts, okay. So this much difference between wave 1 and wave 2, say this is your wave 1 and this is your wave 2, okay. This difference is there, okay. So let's call this difference some, let's say some x, okay. So you will see constructive interference at this screen when your x equal to n lambda. Lambda is the wavelength of these waves, okay.
Yes.
So now we need to just calculate x in terms of d, okay. How do you do that? You see that this angle is theta, right? So can we say that this angle is also theta? Just let me draw it. So we want to find out this distance, okay, and this distance is d. This angle we know, this angle is theta, right? So this angle is pi by 2 minus theta. So this angle would be theta, right? If this angle is theta, this is d and this is my right angle triangle. So what is this distance? D sine theta. Okay. So what is this x additional distance? X equal to nothing but 2 into d sine theta. This is d sine theta. This is d sine theta. So the condition becomes 2d sine theta should be equal to my n lambda. for a constructive interference to be seen at this screen. This is your Bragg's diffraction law, okay? So this helps us to find out this D, and by varying this theta, because theta is in our hand, right? I can change the angle of the electron gun, okay? From that I can get some intensity of that on that screen, intensity on that screen versus theta plot, okay? From that I can calculate some many other informations about the orientation of the crystal and all, okay? Those part I am not going to, just remember this formula, okay? And how this is coming about. So this is 2d sin theta equal to n lambda. So now in the question it is given that lambda is given as 0.5 angstrom, okay? N is given as, what is your N? A second order reflection, okay? Second order reflection means this and this are differed by 2 wavelengths, okay? That means N is 2 and your theta glancing angle is 10 degrees. Theta is 10 degrees. So can we find out that 2d sin theta is equal to 2 into 0.5 angstrom? 2 gets cancelled. So your D is nothing but 0.5 angstrom over sine 10 degree. What is the unit of sine 10 degree? What is the unit of this?
Constant. It's a number.
What is constant? Oh, unitless. You mean to say unitless, right?
Yes, sir.
Okay. So you see, this becomes your, this will come out to be around 2.88 angstrom. Okay. Another observation. What do you think this value should be? Less than 1 or greater than 1? Anyone? This denominator value should be less than 1 or greater than 1?
Less than 1. Sign varies from -1 to 1.
Right, right. That's why you see that this value is increased here, okay? So this is also one thing that what I have discussed in the last class, that your 50 kilo electron volt electron gun, my lambda should be small so that I can measure this range of distances, okay? So this is connected to that problem. If you haven't seen, just watch the problem number 4 I discussed in the last session, and then come back to this and you will find out that okay, this is around 0.5 angstrom, right? So I can measure maximum, because what is the minimum value I can measure? Minimum D I can measure. If sine of this is 1, because maximum value of sine is 1, then minimum value I can measure is 0.5 angstrom only. That will not serve my purpose, okay? So that's why you need to have high energy electron guns. Okay, so let's move on to the next problem. Consider a semiconductor whose energy dispersion relation is this. Okay, so energy dispersion relation or any dispersion relation is, abbreviating I am with the DR, is a relation between omega and K, okay? And energy dispersion relation is relation between E and K. E is energy, okay? So E of K is given as A plus B K minus C square. So we need to assume the mobility is mu 0. We need to find out the mean free time, okay? What do you mean by mean free time?
Average time between two collision.
Right. And why there will be collision?
Due to dispersion.
No.
Randomness.
Right. Everything due to collision, or due to collision there will see, due to collision, there will be randomness in the motion, right? But randomness is not the reason of collision. The reason of collision is presence of something, right? Suppose you are walking in a alley or you are walking in a road. You collide with something. That is a collision, right? You have to have a collision with something. That something has to be present. Some person has to be present or some entity has to be present. What is present here
It's a
in
collision
crystals?
between the collision with the atoms.
Between?
The electron will collide with the atoms present in the crystal lattice.
Electron will collide with the atom.
Because when they are flowing, when an electric field is applied, they will be colliding with the atoms present in the crystals.
Okay, just in this context, just tell me. Suppose there is a atom. Let's say some whatever it is. Let's say some p atom is there. Okay, some doped atom is there. So it has released one electron. It has some vacancy. If the electron collides here, it will get what? It will get absorbed, right? That is called recombination, by the way. So see, these collisions you have seen this chronic penny model you have studied. Okay, I think you need to go through the lectures once. Okay. By the way, just let me tell you, this collisions happens between electron with atoms, or I would say lattice atoms, because at more than 0 Kelvin temperature, there will have some thermal energy. The atom vibrates, and that vibration disturbs its wave function. Okay, or the potential it has around it. So that changes the motion of electron. Okay, that is what is your lattice vibration due to, that is called lattice scattering or
Phonon.
phonon scattering. Phonon is nothing but that vibration only. We are just quantizing it with some particle. Okay, phonon is nothing fancy. Phonon is that vibrations of the atom. Okay. Similarly, electron can collide with other electrons also. It cannot collide, but it can change path, repel and change path. Electron-electron scattering is also possible. Then this can collide with impurity ions, the dopant ions. The dopant ions are charged, right? So it has some electric field around it. Whenever an electron is passing nearby electric field, it gets attracted or it gets repelled, right? So that kind of scattering is also there. So these kind of things introduces this randomness or these collisions. Okay, so these are random phenomena. If you have studied your signal systems, you would have seen that random phenomena can be explained only via some average means, average metrics, right? So similarly, suppose from here to here, if location A to B, the electron can move in time t1, and B to C, it can move up to time t2 and then gets collide and then gets change its direction. So now consider millions and billions of such collisions. Okay, and if you take the average, that average t is the mean time between collisions. That is called the mean free time. Okay, so the formula you must have gone through the derivations, because it will be very difficult for me to explain here. This formula derivation will only take the entire time. So I'll just tell you this much, that this is the formula for mobility. Okay, Q is charge, T is mean free time, M is effective mass. Okay, I will tell you about effective mass in some later question. Just for the time being, understand this much. So you are asked to calculate tau. Okay, tau is nothing but mu into m star over q. Okay, so we need to find out m star. And what is m star? M star is nothing but h bar square by curvature of the EK diagram. That means del square E by del K square. Okay, so this part you have given. So you can easily find del square E by del K square. What is that? Can anyone tell me? if you double derivative this relation, you will get del square E by del K square. What will be that?
Two B
Okay.
dk by
2b will be there, right? Because the independent variable with respect to what I am differentiating is K only. So this will be h bar square by 2b. Okay. So put it here. Mu is given as mu 0, right? M star is h bar square by q into 2b. So your mean free time is h bar square by q into 2b. Okay. So C is your right answer. This proof please see from the lecture, or if you want me to do, you just mention in the comment of that YouTube link. I will post another video. Okay. Even if it is not present in the picture, because it is a complex proof. Okay. The proof which may be taught to you in this lecture is a simplistic point of view. It comes from something called Boltzmann's transport equation. Okay. So just understand this from qualitative point of view, right? If something has a heavy mass, right, its mobility will be obviously lesser, right? A heavy vehicle will have a lesser speed, right? In that sense, you can think it. Similarly, from tau, how can you tell that if tau is more, that means the mean free time between the collision is more. Okay, then obviously you have a better mobility, right? You are mobile without a collision in near future. That means your tau is increased. So that's why your mu should be proportional to tau. This you can understand. Mu should be inversely proportional to something called effective mass. For the time being, you understand it as some mass. Okay. And this q mobility will be this fundamental constant q. Okay. So if I just write from this and this, you will have mu star proportional to tau by m star, and then if we can equate it, the constant comes out to be q. Okay. This way I can tell you the simplistic proof, but for the detailed proof it needs some more depth. So okay, let's move on to problem number 5. Okay, assume that the electron in an n-doped crystalline silicon, n-doped, that means donut type, suffer scattering only due to the lattice vibration and interaction with impurity ions. Okay. By the way, whatever we have discussed here are the scattering mechanisms. Okay. So how many types of scattering mechanisms you know? Can you name them? Anyone can unmute and tell me. Anyone? Name any few scattering mechanisms. You have what is called
Lattice scattering due to charge
lattice
of
scattering due
impurity.
to lattice
No,
scattering.
lattice first, lattice in scattering. Second,
Okay,
due to charge.
that is called also Coulomb scattering or Rutherford scattering. Okay.
Yes, sir.
Okay, then surface scattering. You have heard of this? When two different material, suppose SiO2 and silicon are there, there will be some trapped charges or some trapped bonds. Okay, some dangling bonds kind of thing. Though if electron transports near to this region, this surface, it gets scattered. Okay, the mobility becomes lesser. Okay. So this is called surface scattering. Okay, these are the principal scattering mechanisms. Coulomb scattering and or Coulomb scattering is also known as ion impurity scattering or Rutherford scattering. lattice scattering or phonon scattering. These are the same thing. Okay. Then you have surface scattering. Then you can have scattering due to defect scattering. Then you can have scattering due to grain boundaries. I have already told grain boundaries. Then you can have scattering due to interstitial space. What are the interstitial space? By the way, it is very interesting. Just to let you aware of this. This you have heard of. This you have heard of. This I am sure you will going to heard of. You will be going to hearing about this in MOSFET when you study MOSFETs. So these are the primary. Remember it. But can anyone tell me what are the interstitial spaces? What do you think it should be? Suppose if you have a cubic crystal, okay. So do you think that the crystals are completely packed by the atoms? There will be some void spaces, right? Like in between these spaces where the atoms are not present, these will be void spaces, okay. These are called interstitial spaces. Now suppose you are doing this is suppose let's say silicon, okay, and you are implanting some foreign material, let's say you are phosphorus you are doping, okay. So when we call it dope, when one phosphorus atoms takes the position of a silicon atom, okay, at the lattice point, that contributes to the n-type and p-type doping. But do you think all the phosphorus atoms you are implanting on the silicon wafer or silicon material, all will go to and occupy this site? This will not, right? Some phosphorus atoms may lie at this interstitial space, okay. These interstitial atoms or the dopant atoms, what will be there in the void or the interstitial space, will also create prohibition in the movement of electron, isn't so? That will obviously create, right? It is not lattice, it will not vibrate, it may not be vibrating at the same frequency as the phonons of the lattice, but it will create some obstruction, right, to the movement of the electron. So this is the interstitial space, okay. So there are these many kinds of scattering, but these we do not talk about this in this course. We will talk about only Coulomb scattering and lattice scattering, so that just you are aware that this kind of scattering are also there. I have just mentioned the names, okay.
सर
Yeah.
सर ये ग्रेन इमेजिनरी लाइन होता है ना सर ग्रेन इज इमेजिनरी लाइन
Yeah, right.
how
This
it
is
scat
this is also imaginary line. This line, whatever I have drawn, right, the cubic one, which is also an imaginary line. There is no such line between two atoms, okay. The your question is that how grain as a so see, grain as a line does not create any this kind of thing. You say scattering, okay. So just let me tell you briefly. Why did I tell you? Okay, so these are the grains, right? So this region and this region have different electrical properties, okay. Let's understand it in this way. The electrical fields of these two regions, net electrical fields, will be different. You will learn this in future about polarization and all. Those are very sophisticated stuff for you right now. So just understand this way that field here E1 and E2 are different. So if an electron passes, it sees a change of field, obviously it will get scattered, right? Do you get it? So
yes sir
understand it in this way that the physical line does not do any scattering, but the electrical configuration. In that sense, every force, attraction force, is ultimately electromagnetic force only. Okay, let's not go into there. So these kind of defects are there, okay. So now we are concerned about mainly this lattice vibration or phonon scattering or lattice scattering, and this is Coulomb scattering. Okay, let me write. This is Coulomb scattering, this is lattice scattering or phonon scattering. So if you see the plot of temperature, this is temperature and this is mobility, okay, in log scale. So you would see that these two kind of behavior. I'll explain that in a minute. This is proportional to t raised to 3 over 2. This is proportional to t raised to minus 3 over 2. Okay. And your effective mobility will be like this. Okay. So this one is due to your. Okay, let's find out which one is what. Okay. So one type of scattering, let's say this is one type of scattering, this is second type of scattering, this one. Okay, so we want to find out which one is Coulomb scattering, which one is phonon scattering. Okay, so let's say if temperature increases, vibration of lattice increases, that means number of phonons increases, that means scattering increases. If scattering increases, that means your mean free time decreases, that means your mobility decreases. Okay, so this mobility will decrease as a function of like this. What kind of scattering is this? Anyone?
Lattice scattering.
This is your lattice scattering. Okay, so this is your lattice scattering. And what about this impurity ionization scattering or Coulomb scattering? As T increases, electron velocity will also increase, right? Thermal velocity of electron will also increase. Suppose you have a positive charge center here and an electron is traveling earlier in this way. Okay, so it has scattered like this way because it sees a positive charge. Okay, if sees a positive charge, that means what? I told you in the last class that everything is due to fields, nothing else. Positive charge has outward fields. Okay, so as soon as electron is seeing a field in this direction, so electron will obviously move into the opposite direction. So electron gets scattered from its normal path. Okay, now suppose this electron, as the temperature increases, the electron velocity increases. Okay, so then it will just go past. Okay, if the velocity is very high, then it may get deflected like this, not this much, not this much. Okay, that means scattering reduces. Okay, so as temperature increases, velocity of electrons increases, so the effect of charged particles gets reduced on the path of electron. That means scattering decreases, and that means tau increases, that means mobility increases. In this case, experimentally it was found out that this will be of this form. So this is your Coulomb scattering. Okay, this is your Coulomb scattering. Okay, now this region is very important. This is where we want to operate. We don't want our mobility to change, right? Why don't we want to change? Because you see, if you have studied MOSFETs, for example, you have seen that IDS equal to mu n C ox W by L formula, right? And there mu n we take constant because this is around the room temperature. Okay, So at low temperature, my lattice vibration is not that much, right? That means due to lattice scattering effect is very little. So at low temperature, the dominant phenomena is impurity ionized scattering. Fine. So, and at extremely low temperature region, mobility dash with increase in temperature. So it will be mobility increases. Okay. Mobility increases with increase in temperature. Did you get it? Anyone who have not got it? This is very important concept, by the way. Not for this course, for all future VLSI or electronic courses.
Sir, can you give a point or two to summarize whole of this whole
The
thing?
whole, okay. To summarize, the everything is that there are many. First thing, electron moves randomly and gets scattered due to presence of other particles in a crystal. What are those particles? Those particles are, first of all, other electrons, then then phonons. Phonons means lattice atoms, atom locations, impurities, surface, etc. Those kind of things create scattering. Okay. So scattering has multiple phenomena. What we focus on mainly Coulomb scattering and phonon scattering. Coulomb scattering is due to presence of any ionized charges. Lattice scattering is due to the vibration of lattice points. Okay. Now we want to talk about how this translates to the temperature dependency. You know this formula, right? Mu equals to Q tau by M star. Last slide I have this last problem I have discussed. So how does your tau varies? Okay. Tau means if scattering is more, that means collisions are more, tau reduces, right? Because it is an average free time.
Oh.
So for now, for say, let's take lattice scattering. Okay. Lattice scattering means temperature, as temperature increases, the vibration of the lattice site will also increase. Number of phonons will also increase. That is nothing but the amount of vibration, let's say. That means scattering will also increase. Scattering increases means collisions will also increase. That means my tau will decrease. That means my mobility will decrease. Similar. So that's why this kind of reduction is there. Okay. This is the, you get it right, that if T increases, mobility will decrease from this formula.
Yes, sir.
Similarly, for the Coulomb scattering part, when temperature increases, the electron thermal velocity will also increase. Electron will roam around the crystal with more velocity.
Yes, sir.
If it roam around with more velocity and it sees some positive charges at some other point, it will get less disturbed by that positive charges. So the
Yes, sir.
scattering will be reduced. If scattering is reduced, then collisions will be reduced. Then average free time will increase, mean free time. So my mobility will
Yes.
increase. Okay. Now tell me at which point you did not understand. Did you not understand from this to this place?
Yes, sir. Actually,
See,
there's this different type of scattering I got confused in between.
see this curve you
Now
remember.
I got
Okay.
the point.
Okay.
Okay.
Even if you did not get it, you just revisit this part in the recording. You will get it. Okay. Okay. So let's move on to the next problem. Okay. Did you guys studied about the chronic penny model?
Sir.
Okay.
In lecture,
So
sir has explained.
yeah, lectures he has explained, right?
Yes, sir.
So in the chronic penny model, what happens? First thing is that you have periodic atomic arrangement. Okay. If periodic atomic arrangement has a potential profile like this. Okay. So the net profile would look like this, 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 and then go on. Okay, so this thing we can approximate as a rectangular potential well, periodic rectangular potential well. Okay, so if I just draw this, it will be in this fashion. Okay, here are your nucleus of the atoms, and electrons can occupy some energy levels. We have seen that for potential well, right? That energy levels are discrete. And then suppose you have this kind of thing. Okay, generally it is an infinite periodicity consider. So how do you do what chronic penny did is that this kind of profile they approximated with a rectangular potential well. Okay, potential periodic potential well. So let's say this is x equal to 0, this is x equal to b, and this is x equal to minus c. Okay, so what is the period or lattice constant? This is b minus of minus c equal to b plus c equal to a, let's say. Okay, so now if you solve your Schrodinger equation at this place and at this place and this place and at this place, you will find out some particular condition. Okay, what does that particular condition lead to? This particular condition will lead to some energy relation with some cos k of a term. Okay, so if you simply plot this f of e term with respect to energy, right, you will see this kind of nature. As your cos, this right hand side lies below plus minus 1, so the solution must be lying below this plus 1 and this minus 1. So whatever is lying between this are the valid solution. Okay, and these are the invalid regions. This translates to the energy gap in the crystal. Okay, so if you have not gone through the lectures, it is very difficult for me to make you understand this thing. So that's why I always request you, at least if you did not attempt the assignments, just go over the lectures, then you can ask question on this kind of very in-depth discussions. Okay, so you see what happens is basically that these locations, if you translate it to k domain, see for example this location is k equal to uh, let me tell you in another way, that these are your band gaps. Okay, band gaps or forbidden, these are your allowed energy levels. Okay, because the solution lies between plus 1 and minus 1. So for cos ka to lie between plus minus 1, we have that ka should be equal to n pi, right, at this boundaries n pi, because at these boundaries we have the band gaps, right? At these boundaries we have this band gap when this function crosses plus 1 or minus 1. So for the value of k, it will be n pi by a. Okay, and n can be your plus minus 1, plus minus 2, 0, and anything. Okay, so basically these values of k leads to energy. At these values of k, you will have your band gaps. Okay, you must have seen that this kind of EK relation if you have gone through the lectures, that this is pi by a, this is minus pi by a, this is 0, and then let's say this is 2 pi by a. Okay, so you will have something like this. then you will have something like this. This kind of band structure, these are called band structure or EK diagram. Okay. So these are the energy gaps. This happens at these locations, k equal to pi by a or integer multiple times of pi by a. For example, if you want me to point out at this diagram, this would be k equal to 0. These 2 points would be k equal to plus minus pi by a. These 2 points would be leading to k equal to plus minus 2 pi by a. Okay. So to solve this question, at k equal to pi by a, sorry, it is real, not real, right? N should be integer. This would be your right answer. Okay. Where do you observe the energy band gaps in the energy dispersion graph? This is the energy dispersion graph. Energy dispersion graph. Why this is called energy dispersion graph? Because I have already told you earlier that energy dispersion relation, EDR, is the relation between E and K. Okay. So the graph of between E and K, graph between E and K is called the energy dispersion graph. Okay. So this is also called expanded zone representation. Okay. So at this locations of K, you will see the band gaps. Okay. So let's move on to the next problem. Please go through the lectures. Please go through the lectures. Okay. Then you will understand. Then come back and visit this thing. You will see that you understand this thing very easily. Okay. So what is a Brillouin zone? Brillouin zone, by the way, let me just this is a Brillouin zone. Okay. This is another. Okay. Let's say this is your another Brillouin zone. Okay. So basically what happens is that this is a set of solution of the Schrodinger equation. Okay. Let me put it in this way. This is another set of solution. So this is called your first Brillouin zone. This is called your second Brillouin zone. These two. Okay. So what are the Brillouin zone? Basically, Brillouin zone, let me see the options. A region of K space that contains all the unique solutions of the wave equation. Okay. A region of K space. K space means this is K axis, this is K space. A region in K space where you have all the solutions. Okay. It can be explained in other way also. If you have studied that, what is real space, by the way? Real space is X, Y, Z, right? Or let's say L in that matter. If that this box per only box you have considered, this is X equal to 0 to X equal to L. So this is real space where we have the physical dimensions, right? And what is K space or reciprocal space? That is nothing but 1 by L space. Okay. So or meter inverse space. Can you tell me any of such kind what you have encountered? Obviously you can answer because K is your 2 pi by lambda. Okay. Lambda has a unit of meter and 2 pi has a unit of radian or unitless. So K space we called as a reciprocal space. Reciprocal space or K space. Okay. In this or in this sense also you can tell the Brillouin zone. And how do you calculate that Brillouin zone? For example, if you take this much, let's say if you have this and you connect all this is a atom, you connect all the atoms connecting to that line and you take the perpendicular bisector of these lines. Okay. Then and you connect those things. This is there in the lecture number 9. Okay. So I'm just for the sake of completeness I'm telling. So you will find a space something like this. This is called your Wigner-Sees cell. and if you just do the Fourier transform, then you will get a 1 by lambda kind of stuff, right? That space translating into the K space will give you Brillouin zone. This is the same stuff whatever has been discussed here. Okay, I am not going into detail due to the time constraint. Please see lecture number 9, I suppose. Just see in the lecture 9 in the that thing, you will get an idea of what Brillouin zone is. Okay. So by the Fourier transform, you know that, right? Time to frequency domain, you do Fourier transform. Anyone does not know about time to frequency, it is Fourier transform? Anyone who knows that by Fourier transform we can go from time domain to frequency domain?
Yes, I know it's in engineering mathematics.
Okay, right. So what is frequency? Frequency is nothing but 1 over time, right? Do you agree?
Yes, sir.
Similarly, if lambda space to K space you want to go, or this is real space and this is reciprocal space, you also do the same thing. Okay, same Fourier transform you apply. Okay, I think this much is enough for you to solve the problems. Okay, just remember that it is the region of K space that contains the unique solutions of wave equation, that this region. Okay, then moving on to the next problem. Yeah, this is an interesting problem. Consider the 1D band structure. By the way, EK diagram is also called band structure. Okay, EK diagram, band structure. Band is what? Energy band, right? And this is energy dispersion graph. These are the same stuff. Okay, so there I have given us this kind of function. This is E, let's say this is K. By the way, Kx, this K axis is a vector. Okay, K is a vector of K is a vector of Kx, Ky and Kz. Okay, so any point here, if I just simply write K, has meaning of that this is a 3 dimension. Okay, let's say 1 0 0, it is a particular location in a 3 dimension. Okay, so in this problem they have given that let us consider only Kx. Okay, so Kx and E of Kx. Okay, only 1D they are talking about, and they are given something called this kind of band structure. Okay, this is your HVF mod Kx. Do you see why I am drawing like this? What is the graph of y equal to mod x? Can anyone tell me? What should I draw here?
Same, that V.
Same, right? So you see, what is my effective mass definition? H bar square by the curvature of
That
this, right? So does curvature exist at this point?
No, sir.
Derivative doesn't exist, right?
yes.
So this quantity does not exist. Okay, if this quantity does not exist, how do I say that this quantity does not exist? What will it happen? If I take the derivative, let's say if I take E bar Kx and here is Kx, how will the derivative look like? Can anyone tell me? This is plus something, plus what? HVF. This would be minus HVF. There is a discontinuity, right? And we have seen that this kind of unit step function, or this is not actually unit step function, this kind of step function has a derivative of delta function, right? Which is not real. If this to this derivative you do, you will find some delta function, right? That means that function, that derivative does not exist. That means your effective mass is not defined. This is actually a practical case, by the way. You see, you generally do this parabolic approximation of the energy band diagram, right? But there are certain materials, if you have heard of graphene, graphene shows this kind of band structure, okay? It does not have any effective mass. By the way, on this note, why do we need effective mass? Anyone can unmute and just tell me. We have very short amount of time. Why do we study about effective mass?
To calculate mobility
And why do we calculate
We are
mobility?
taking into account the relativistic
and
effects.
to know the flow of electron, moment of electron.
Right, that is called, we need M star to know carrier transport, okay? The term is carrier transport. This you will be learning in the next few lectures. We want to know how a particular charged carrier move in a crystal, okay? Be it electron, be it hole, how does it move in a crystal? That's why we want to know about the transport, how they transport through the rods of the crystal, okay? So that's why we need mobility, that's why we need M star. By the way, Srihari, this is not the same thing of that relativistic thing, okay? This M star is your effective crystal mass. You see, in free space, electron moves with a mass of some, say, let's say M0, okay? In crystal and in free space, electron does not, what is free space? There is no force acting upon the electron. That means electron is having only kinetic energy. That means your E is nothing but h bar square k square by 2m. Fine. And what is this EK relation? E is, let's say, y equal to x square, y proportional to x square. This is nothing but your parabolic relation, right? This is for free electron, but for crystal, you see the structure is like this. It is not actually a parabola, okay? It is parabola for this very small region. Just let me explain this stuff. Suppose this is the crystal EK diagram, okay? And your free energy electron diagram will be like this. This is your free electron diagram, okay? So how do we why do we do about this parabolic approximation of effective mass? This is because at this part of the location, okay, we can approximate the crystal EK diagram like a parabola, but for a very small part at the bottom of the conduction band. And my electrons, when residing here, I can approximate it with a parabolic approximation. So effective mass means that mass in the crystal of electron for which the parabolic approximation is taken into consideration, okay? So it is not the same thing what I had told you with the Lorentz factor correction and all. These two are not the same thing, okay? This is the mass of electron in a crystal. This will not be same whenever it is in a free space, okay? Let's understand this in this way, okay? Please, I request you all to go through the lectures again, okay? Because these are very critical concepts and you may miss something. So please go through the lectures again, okay? These two questions I am skipping today. These are pretty easy questions. This we will do in the next class, okay? This we will do in the next class. This is related to some packing density and this is some block wave function, okay? Let's end the session here. And I am giving you two more references you can follow. These are advanced references, but very good. The writing is very good so that you can understand this concept very quickly, okay? John P. McKelvey book, Okay, 1955. You can download it in all. I think it is available online also. Okay, so that's about it today. You can write this quantum mechanics part and this kind of transport part from this book. It is very good. Apart from the SMG book, which is the core standard reference to this course. Okay, for in-depth understanding, you can refer this book. So, okay, any question you have today, whatever you have discussed so far? You must be having so many questions for the latter part of the thing. But for that, I request you to go through the lecture once, then come back to this recording video and then try to relate the things. And then if you do not understand anything, tell me next week. I will again explain this part. Okay. Anything you have difficulty or difficulty in understanding, visualizing, any doubt. Okay. But these are very critical concepts. You need to understand this very carefully. And once is enough. Once you understand this carefully, it will retain for the entire time of your life. Okay. So any question you have? Okay. If not, so thank you everyone. Let's end the session here.